Okay, okay. We're going to start with the easier one today. One quick simple concept, and that is, what if your representative rectangles aren't vertical? Easy. So let's take a look at that. Horizontal rectangles. So you might be saying to yourself, Self, why would I do that? I can do it with vertical rectangles. I did the day 51 homework okay with vertical rectangles. Why would I ever use horizontal rectangles? I will answer that question shortly. So today we're going to do the stuff we did the other day. We're going to do the other stuff we did the other day, but change the rectangles to be horizontal. And then we're going to replace x's, with y's. And then your last goal for today is to get a job or get into college. Which one do you want?
Just up into college.
College first. Then you go to work. U of I. Excellent. Dimitri's going to U of I, everybody. And he's going to study business. Do you know which business? You're leaving. Okay, that'll be good. Make it bank. MBA in the future. A lot of schooling. But you're a first man. Let's move on, Joey. Blah, 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 representative rectangles, vertical, horizontal. Why would we use horizontal rectangles? I have an example for you. Let's suppose we have that problem. Okay, now, first thing you'll notice, my equations are funky. Okay. And notice I use the word equations and not functions. Why wouldn't I use the word functions? Did I make a mistake? Yeah.
There's like 2 points for, like 2x points for every y.
Meaning that these are not,
It's not a function.
these aren't functions, right. They're sideways parabolas. They look like this. So we're using equations, but just because we're using equations doesn't mean we can't find the area that's bounded by those two parabolas. Okay? If this was given to you in terms of y, let's say, for instance, I solved the red one for y, we would get y equals the square root of x, and you just get the top part. I don't just want the top part, I want both parts, so I put everything in terms of x. Okay, regardless, I've got this picture. You can all see the region that we want to find the area of, yes? Okay, so a couple questions. What do you notice about that region? Makes for good audio. What does this mean, Lauren?
What do I notice about, like, well, it's, the thing on the top and the thing on the bottom are the same, but.
Ooh, okay, well, hold on. So how can that help us?
So they cancel.
No. Remember, we're doing area, we're not doing just antiderivatives. So the area below, it wouldn't be, I'm not going to give you a problem that's just 0. I mean, we'd be out the door, I'd be at Starbucks already.
So,
Remember, we're doing area, so area below the curve, or below the x-axis, is still positive.
okay. So you only need to find half.
We could do it that way, yeah. We could find just the top half and double it to get the bottom half, and we're good to go. Were you going to say something else then before I interrupted you? Okay, good. Any other comments? Okay. If we were going to solve this problem the way we did it on day 51, how many representative rectangles would I have?
3.
Say again?
3.
Perfect. 3. Does everybody see why there's 3? I got them right here. So the region from -4 to 0 requires one representative rectangle. The top part is the top part of the blue curve. The bottom of the rectangle is the bottom part of the blue curve. All of a sudden I get to 0, and remember the rules. If the top or the bottom changes, we need another representative rectangle. Now, this is all based on the idea that we're not using Lauren's excellent idea, just do the top half and double it. We're going to find the whole thing. That's what's causing problems. Yeah. No, we're going to do the whole shoot match. Okay. So then, we get 2 different representative rectangles, one for the top part, one for the bottom part, and then we go crazy. Could you solve it that way? Yes. Is it a pain in the butt? Yes. Do we want to do it that way? No. That's why we're doing it today, because if I draw my representative rectangles horizontally, you can pretty much figure out where I'm going with this. How many rectangles do I need? One. It looks like that. Don't know why I use yellow, because it's so hard to see. You all see that yellow guy, right?
Yeah.
If I start that yellow guy up at 4,2, and I start moving through that region that we're looking for the area of, we don't care about top and bottom anymore. Now all of a sudden we care about the left-hand blue parabola and the right-hand red parabola. And neither one of them changes through the whole area. So I'm good to go with just one integral. If this is confusing to you, turn your head 90 degrees. It's the exact problem we did yesterday, 2 days ago. It's just turn 90 degrees. When you turn things 90 degrees in a graph, what does it change? Go.
X and Y.
X and Y's become, they replace each other. Okay. In other words, if I go back to that problem and I change the red function to y equals x squared, and I change the blue function to y equals 2x squared minus 4, it'd be easy peasy. This is the exact same thing. Okay. So we got to remember two things. Number one, all the x's become y's. And number two, instead of doing top minus bottom, any guesses? Right minus left. Okay, I have that. Hold on. We'll come back to that in a second. Click, click, click. I'll come back. Top minus bottom is Tuesday. Today, right minus left. Excellent. And it must be important because it changes colors. So let's go back and look at how to solve that problem then. Okay, we got that. We got this. Okay. I'm not going to trust the picture, so the first thing I do is I find the point of intersection between the two graphs. It happens at plus or minus 2. You know that from looking at the picture, but again, I'm not going to trust the picture. I'm not going to trust my calculator. I'm not going to trust Desmos. I will trust the algebra, though.
Oh, I never.
You good?
Yeah.
Okay. So, when we're doing the representative rectangles when they're horizontal, when we're looking for our limits of integration, the question you should ask yourself is, where do I start on the left and where do I end on the right? But now with horizontal rectangles, you're asking yourself, where do I start on the top and where do I end on the bottom? So my very first rectangle is going to be all the way up at y equals 2. Because remember, we're working horizontally now, so everything is in terms of y. Okay, I don't care that those points are 4, 2, and 4, negative 2. All I care about is 2 and negative 2 in the y terms. So I got the points of intersection. Then I set up my integral. There's the area of my rectangle. Now we're talking about the height of the rectangle actually being the width of the rectangle, right minus left, red minus blue. And the thickness of that rectangle is really, really tiny, almost 0, which in this case we call dy. And then I just add them up. That's the hard part. If you can get the area of the rectangle, the rest of this is easy. Because all I'm going to do then is take rectangles from 2 to negative 2 and be done. Now if we use Lauren's suggestion, we would go from 0 to 2 and double the answer. I'm going to give you a second to finish writing and then I want to talk a little bit more about this. And I want to explain why I like Lauren's idea a lot more than what I have up on the board.
Why are we doing functions, or with non-functions at all?
Because we're still looking for areas, and sometimes those areas are generated by things that aren't pretty functions. Like when we get a little deeper into this stuff, we'll be working with circles again. even though circles aren't functions. Because it's
That
getting
makes
us,
sense. Okay.
because we're getting the things that generate area, even though those things that are generating the area aren't functions.
Yeah, okay, that makes sense with circles, I guess. Yeah.
All right, so here's the question. Why would I prefer to use Lauren's method of going from 0 to 2 and multiplying it by 2 versus the method I have there of -2 to 2? Done.
It cancels. I got 0, but I don't know why.
I don't know why either. You shouldn't.
Okay, that's strange. I can maybe
Okay. Anybody else? Most of the time, plugging 0 in.
I was gonna say I trust Lauren's opinion and judgment and everything, so.
Wow, that was very nice. Okay, good. So you're just gonna trust Lauren blindly because Lauren's Lauren.
Yeah,
Okay.
you should see her car decked out for Christmas. You'd follow her anywhere too. It's adorable. Your Christmas lights, I love them.
moments where do I just let it go, or do I pursue and go down this rabbit hole?
Oh, I forgot to
What do we
take the
think?
integral.
No, pursue that one.
That's why.
Usually plugging 0 into a function is going to give you a nice, easier answer, because look, if I plug in 0 there, I just get 4, as opposed to plugging in -2. Are you incapable of plugging in -2? No, you're all smart fellers, you can handle it, but sometimes your life can be made easier if you're a little sneaky about it. They'll both give you the same answer. I don't know what I'm guessing you probably made a sign error.
No, I just didn't take the integral.
That still makes sense, though, doesn't it?
So you just plugged into it, then you went crazy on it. All right, but we're also gonna pretend that didn't happen. We're done with the first half, okay? Any questions? Don't overthink this, all right? Horizontal rectangles can be your friend, just switch everything. Oh, you might be asking yourself, how do I fn int if it's in y? In other words, how do I fn int that? On the bottom. Any guesses?
Exact same thing. Just in the Y.
You could plug in y as long as it ends in dy. You don't even have to bother. Just type it in like that, but I'll change all the y's to x's. It's the same thing.
Yeah.
All it did is take the picture of the parabolas and tilt it 90 degrees. You could actually fn int using y squared minus 2y squared minus 4 in parentheses dy.
Wait, can
Yeah. Why would I lie to you? Have I ever lied to you before? I've never lied to you. Why would I start now over something stupid like that? And if I was going to lie to you, it would be on something relevant like the fact that you owe me $20. Yes, it'll work. It'll work as long as the variables match. What you can't do is y squared minus 2y squared minus 4 dx.
Right. No, I mean, how do you do it on a calculator?
You have all 26 letters are on your calculator.
Oh, you use those there. Okay.
Beautiful. All right, we good?
Yes.
All right, second shot.
Come over here, close this.
What would happen if you went left or right?
Ooh, great question. The same question. I would answer your question with another question. What would happen if you went bottom to top? How would it affect your answer?
Oh, you just get like the area. Like, it would just what makes sense.
It'd be negative.
We don't have, we didn't post,
I'm sorry?
we didn't post these.
The slide.
Oh.
Sure.
I'll do it first.
How's your day been?
Don't get old, kids. Not good. It's been a busy day. They have to drive one of our kids because they were sick. Yeah, they couldn't drive. They had vertigo, and if they drove, they could crash their car. So I had to drive them home with them in the front seat going the whole way home. And they don't live close. Since you asked, just had to tell you. Okay, here we go. Average value, also known as the mean value theorem. We've heard the mean value theorem before. We have MVT already. What are we doing? Well, it's the same thing, except now it's for integrals. Just like we had the fundamental theorem of calculus for derivatives, and then we had the fundamental theorem of calculus part 1 and part 2 for integrals, same thing is true here. I think I've mentioned this before, but it warrants mentioning again. Anytime a function or a theorem has its own name, it's going to be important. It's quote unquote note card worthy. This one is not that complicated. In your notes, after the mean value theorem or after average value theorem, you might want to write down meltdown theorem. I call it the meltdown theorem. I'll explain why in a second. Okay, here's a joke for you. I'll give you a second.
Oh.
Now, not only is this a nerdy math joke, which is always fun, but there's actually some legitimate learning here. Who wants to explain the joke? Liam?
Because it's in terms of n, so you have to multiply n, so it ends up being aspirin, right? Like, yeah.
And? You missed half of the
Oh,
joke.
plus c. Oh, yeah, okay.
Yeah, it's an indefinite integral, so
Yeah.
you gotta stick a plus c on that.
Mhm.
In that equation, what are a, s, p, I, and r considered? Constants, correct. So think about it as taking the integral of 2 dx. The integral of 2 dx is just 2x plus c. So the integral of aspiri is aspirin plus c. Thank you. That's all I needed. Moving on. We're going to talk about the meltdown theorem. We're going to talk about MVT, which is kind of the same thing. I don't even know why I put that in there. What? Can you all read big words too?
Like what kind of big
Excellent.
word?
Huh?
Like what's like the biggest?
Multisyllabic words. Things bigger than like dog.
So like most days.
Most days, okay. Beautiful. Okay, here we go. So let's suppose you got a glass ice. And it's a cylindrical glass. I know I'm kind of reading things to you, I'm sorry, and I just told my ed kids the other day that I hate when people read slides to you. So I'm not, read that, we'll come back to it. I don't want to read it to you. I found myself going down that path and then I realized I was being a
That's why
hypocrite.
you put your whole story.
Yeah, oh yeah, there we go. I still don't know why I put MVT in there.
Spell it.
Spell MVT. Unless I was intending to be funny, which it wasn't. All right, you with me? Okay, glass of ice. The top's all scrambled. What happens when that glass melts? Say again?
It all just becomes even.
It all becomes even. Correct. Okay. Now, that level that you get when the ice melts is what's called the average value. So we're going to use that analogy to explain the mean value theorem, or the average value theorem. And that is, we take a function and we put it in an interval. So you think of the function as being the ice, and the interval is the sides of the glass. I got a picture right there. So there's some function, it's red, and I put it in a glass. The sides of the glass are A and B. When that function melts, hence the reason it's called the meltdown theorem, it will level out. Where does it level out? It levels out at that horizontal line called f of z. Everybody with me so far? Okay, so here's the question. When this puppy melts down, you'll notice before it starts to melt, I've got 3 regions. I got a green region, I got a blue region, and I have a purple region. What can you tell me about those 3 regions? How do they relate to each other? Right?
Is blue equal to purple plus green?
It better be, yes. Okay. The blue region, the stuff below the average value, should be equal to all the stuff above the average value. And that's kind of working backwards. That's assuming that we know what that melting level is. You don't know that when you look at your glass of ice. You don't know where that line is where you're going to get water. So we're kind of putting the cart before the horse. Okay. But that's the idea of what we're doing. It levels out, it finds the average value, hence the term average value theorem, of the function. If I go backwards from f of z, from that water level, it hits the original function in 2 spots. I just highlighted one of them. Okay, I don't want to say obviously, but there's another point over here. So I should have done this. There's 2 different spots where it hits. I just wanted to talk about the other one. The z term is the x value of the function that generates that average value level. Okay, you go up, you hit the function, you move over to get the y value. All we're going to do now is go backwards. Go from the y value over to the function, go down to the x. You should be able to do either one of those. If I give you a function and I give you the x value, you can tell me the y value. If I give you a function, give you the y value, you can tell me the x value. Is this making sense? Okay. How do I do that? No. Oh, it's easy. We could find that whole area under the curve, right? You know how to do that. How do I find the area under the curve? Take the integral of the function from a to b.
Are we assuming half the function?
Yeah.
Okay.
Yeah, I'm going to give you a bunch of information. Blah, 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 blah. Average value, we talked about that already. There's my f of z. Then you find the z over there. Great. How do we do it? We use that guy. So literally what you're going to do is find the area under the curve and then take the average of it. How do you find an average?
Add all numbers and divide by non-numbers.
Right. So what we're going to do is take all the area and divide it by the range that that area is covering. So it's going to break it down into an average. You have 6 items, you add up the 6 items, you divide by 6. You have an area that goes from A to B, you divide by the length from A to B. Add all that area up and divide by A to B. 2 different versions. I like the top version better. However, the bottom one is more of a standard way to write it. But I like the top one better again. Take the area under the curve and multiply by 1 over b minus a.
It's your fave.
I am totally going to use that from now on. That's... You just teach the rest of the class. I'm just going to sit here and watch you work. That was exceptionally well done. Okay. Wait till I show Everett that. He's going to be so jealous. But I'm probably going to have to explain it to him. He's not the sharpest tool in the drawer. No, sharpest tool in the shed. Sharpest knife in the drawer. Yeah. Okay, let's move on. Another picture illustrating the same thing. Depending on the source that you're looking at, they like to change the notation. Sometimes it's f of z, sometimes it's f of av, sometimes they'll put an e on the end to make it your fave, but mostly it's av. Okay, it's the average value of the function. I've even seen the College Board switch back and forth between f of z and f of av. So I just wanted to make sure you understood both of those things. Okay. So again, it illustrates what we talked about in that left one with the purple region. The blue stuff at the bottom, below the average value, is going to be equal to the pink stuff above. The right picture, the hashed part of the white below the blue line or a green line is going to match this region up here, this little triangle looking thing up here. They should be the same area if that's the true average value. Okay? That's all the theory. I think in this problem, the theory is a lot more difficult than the application, because you can all take an integral and you can all multiply by a simple number, right? All right, so let's try an example. Here we go. Let's do this. Bust out your Desmos and graph x cubed, and make sure you can see the whole graph from 0 to 4. So pinch and spin and do whatever you need to do to get that. And I'm going to ask you to try something without cheating, because I know you have the slideshow here. I don't know if you, I don't remember what I gave you on your slideshow. But once you're looking at the picture of that part of that cubic, find the region we're talking about. Okay, we're talking about the region from 0 to 4 below that cubic function. So it should be this weird, big, tall, skinny, triangle looking thing. You with me? Looking at that picture, draw a horizontal line about where you think the average value would be. Where can you draw your line through the, do you understand what I'm talking about? No? Okay. I'll explain. Okay, the function looks something like this, yes? So the region we're talking about is this guy over here. Now you see that on your graph? Yeah? Okay, good. So my question for you is, if I was going to draw a horizontal line through this region, where would I draw it so the top and bottom match each other? Okay. In other words, let's suppose it's up here. I draw it up there. I think that's where it is. Well, that's a ridiculous answer. Why is it a ridiculous answer? Because there's no way that that matches that. I obviously want it a little bit lower. So guesstimate where you think that value would be. And then we'll see how you did.
From where is 4?
0 to 4. So I did the math for you already, and I told you that that area under the curve between the graph of x cubed and the x-axis has an area of 64. Its average value is then, where are we at? Is 16. Now, why is it 16? If the area under the curve, or the integral from 0 to 4 is 64, we multiply by the range, or I should say the domain. The domain is 0 to 4, 1 over b minus a. And that tells me that the y value would be at 16. So let's stop for a second. Do you all understand what that number represents? Is that an x value or a y value?
Y value?
It's a y value. That's the, if we go back to this picture, that's the spot where I would draw my horizontal line. Where this region would match that region. This happens at 16. Okay, now does that make sense? Okay, good. The last question is then, where's this x value? Because that's where it hits the graph. If I go backwards from 16, I hit the graph there. How do I find the x? Anybody? Nathan?
You plug in 16 for y.
Beautiful. If my function is x cubed, y equals x cubed, I set x cubed equal to 16 and solve for x. What is that value, Nathan?
2.92.
How'd you find that?
I use those.
Oh, you cheated on decimals.
Yeah.
Excellent, well done. Anybody else? It's a cubic root of 16.
Oh, thanks.
So as Nathan said, I'm using z instead of x, but it's still the same thing. It's the value from the x-axis, and then you take the cubic root of that to get 2.519. That is not hard math. Should not be. The concept, however, can be a little tricky. If If I take that function of x cubed and I melt it down, it will level off at 16. You'll get a nice, cute little rectangle. That rectangle will be 16 units high and 4 units wide. And that's the important part to consider. If you look at the top of this slide, from doing our calculus, we know that the area of that triangle, weird swoopy looking thing has an area of 64, because that's what the antiderivative tells us. What the average value theorem says is if I melt all that down, I get a little rectangle. That rectangle is 16 units high and 4 units wide. It has the same area as we did underneath the curve. Okay? Questions? I believe we're done. We are. Day 52 for homework. On Wednesday, when we come back, we'll spend some time going over the day 52 homework, and then I'll have a quick quiz for you. It will not take probably more than 30 minutes. On your homework, I would practice drawing your pictures from scratch. Don't rely on Desmos or your calculator too much. Most of the functions that you're dealing with on the homework are straightforward, easy functions you've seen before. X squared, x cubed, the square root of x, etc., or lines. Okay, that kind of stuff. Get used to drawing them by hand because you're going to have to do that at some point in time. And even if you're still fighting me on the representative rectangles, I can't encourage you enough to get in the habit of using those. Okie doke? Questions? Hot diggity. In the immortal words of Dr. Seuss, go dog go.